Okay, now I'm going to go on to the second talk. Totally different topic, and this is kind of my favorite topic, so please ask questions on this. It's about synchronizing of clocks. Obviously, a software clock is essential to just about everything. First of all, we need a fundamental hardware support, for example, a timer chip. We need to be able to synchronize the clock, and of course, time stamping, which is a separate issue, is also essential. We need inexpensive, we want it to be inexpensive in terms of hardware, inexpensive and especially convenient in terms of synchronization, and of course we want it to be accurate and robust. The current solution is NTP-based synchronization of a standard software clock. It's really not good enough in two important ways. First of all, this solution does not care about the rate of the clock. In fact, it deliberately varies the rate in order to track the error, that is called the offset, of the clock to zero. But in fact, a smooth rate of a clock is an essential requirement to be able to measure delta t's. And delta t's, in fact, is what you do most of the time. When you measure time, you want to measure delta time. It's also not robust in terms of shifts. Sometimes shifts as large as 1 second, offset adjustments are made, and that can really do horrible things, especially to network measurement. We can do better because in the past, the current philosophy is based on the idea that the local clock is terrible, so we must ask the expert. But the reality today is that the local hardware is excellent, and we should be trusting it and using it. We simply have to calibrate it. We still need a reference source. We're still going to be using NTP servers and using the NTP protocol to communicate with them to get timestamp information. But now we recognize that the local clock hardware is fundamentally good, and the idea that rate is important, not just offset, it changes everything in terms of filtering and how accurate and robust we can be. So in this talk, I'll tell you about how we can define both rate and offset synchronization. The idea is extremely simple. We use a CPU oscillator as a clock. We have a TSC register which counts CPU cycles. So the idea is two different clocks based on this very simple idea that we have a pure frequency. Okay, I'll call it the simple skew model. First idea is a difference clock for measuring delta t's. You simply take the delta reference register value, multiply by the period of the oscillator, and that becomes a delta t. Simple. For the absolute clock, you need to add in a constant to correct that value up to real time. Fundamental advantages are you have a register that's already up to counting cycles on hardware, extremely fast to read it, naturally high resolution, like 1 nanosecond for a gigahertz processor. You get those for free. The catch is you have to measure that P and that theta naught, of course. And the real catch is theta naught is in fact not a constant, but is time varying. We need to track the drift. Everything's based on the quality of the hardware, as I said. Just to cut a long story short, this idea of having a pure frequency for the oscillator works incredibly well. Over periods of 1,000 seconds, it works extremely well. And for periods below that, the relative error, the variability in the rate, is still only 1 part in 10 to the minus 7. So what we have is extremely smooth rate of our hardware, of this oscillator, and we've got to take advantage of that. The basic scenario is to get the timing information, we have an NTP packet that's sent. When it leaves the host, we read the TSC register. It goes to the server, a timestamp in seconds is put in. It leaves the server, another timestamp in seconds, returns to the host, another timestamp in a TSC register value. So that's 4 numbers for each packet. That's the raw data. But we need to assess when are the timestamps there reliable and when are they not reliable. We do that using round-trip time-based filtering. Here we see a time series of round-trip times. We see they have some kind of common minimum level with occasional positive excursions. Those excursions are due to delay in switching elements and other effects. Basically, our filtering idea is based on measuring to what extent those round-trip times are above the minimum value. Now let's go ahead and try and measure that P. Using that basic relationship with the deltas, we invert that to get a measurement for P. We call that the naive estimate, and I've got that in green there. We see that very quickly it closes in and becomes very close to the black reference values. You notice that the scale there is already only 1 part in 10 to the minus 7, so we're looking at small variations. But we see spikes, and those spikes are due to network congestion, and they can be really problematic. We need to get rid of them. How do we do that? What we do is we look at the packets, and if the quality is good with respect to that round-trip time filtering, then we use them in the estimate, and if they're not, then we don't. We're just patient and we don't. The result is we see there that the errors trend quickly below the dash line. The dash line is that 1 part in 10 to the minus 7, and it never returns. Now, to put this in perspective, in only 10 minutes of calibration, you have a value of P that's accurate enough to make delta T measurements over small intervals more accurate, or as accurate, as if you had GPS directly attached. And if you then remove connectivity from the server for a week, it would make absolutely no difference. So this basically eliminates the need for GPS for delta t completely for delta t measurements. Now for the much harder problem of absolute synchronization. Again, we can come up with some naive estimates which disregard the effects of network congestion. Again, we see that the green naive estimates are pretty close to the black. I hope you can see the black. That black line is tracing through the middle of the green there. But again, when network congestion events occur, we get these spikes and we want to get rid of those. How do we do that? Well, if we want to measure at a given time t, what we do is we look back in the past for some windows, say 1,000 seconds. We look at the naive estimates in there, and we weight them according to the round-trip time-based quality, and then we take a weighted average. That's what we do. That's the basic algorithm. Now I'm going to show you a close-up of the results. The green are the naive estimates. The black are the true error of the clock, measured with our reference system. We have a GPS synchronized reference system, hardware-based. And the blue is the output of the algorithm. We see that the blue tracks the black very well. In fact, it maintains pretty much a constant distance, and that distance is only 30 microseconds. Now, the fact that distance is constant is very significant and points to a key issue in this whole synchronization game, and that's the path asymmetry. The path asymmetry is simply the difference with the delay to the server and the delay coming back. In practice, you cannot measure this delta, and so we assume it to be zero. But if it's not zero, that creates a problem. But it is bounded by the round-trip time. So in this particular case of the server int, we used 3 different servers, but the results I showed you were from the server int, which was only 1 millisecond away on campus at the University of Melbourne. Its delta, its path asymmetry, was only 50 microseconds. This means that the best we can possibly do by any algorithm, this is fundamental, this is not our algorithm, this is any algorithm, the best any algorithm can do is to measure the offset to 25 microseconds. And our median error was 28 microseconds. So we see that in terms of filtering, we were being extremely successful, but we couldn't get around this fundamental problem which all methods would suffer from. The only way to get around that is through the choice of server. You want the server to have a small round-trip time, and especially you want it to have a symmetric path. Now, in a full robust system, it needs to be robust to many, many factors. A key motivation was to be truly robust in the real world. We need robustness, and we have robustness to changes of the oscillator over time, changes in temperature. It's extremely robust to packet loss and network congestion, as we've seen, even time stamping errors and server errors, which are the most serious of all. We also have a very nice way to get around the problem of level shifts in round-trip times. This can occur, for example, if there's a route change to the server. Since our filtering is based on round-trip time, it's extremely important to be able to take that into account efficiently, and we've managed to achieve that. Here's some examples. On the left-hand side, a polling period with a polling period of 64 seconds, so the NTP packet, 1 every 64 seconds. This is the histogram showing 99% of all values. This is over a 3-month period, and in this period, some nasty things happen. For example, there's a period of 3 entire days where we didn't collect data, and that's included here. Despite that, the median error that we made, we're making a measurement for every packet, is only 31 microseconds, and the interquartile range there is only about 15 microseconds. So this is pretty robust. On the right-hand side, we get similar median error, but a bit more spread when the polling period goes up by a factor of 4. The algorithm, of course, has some parameters in it. We want the performance to be insensitive to those parameters. Here's an example here. This is the main parameter, that window size I mentioned. Here it varies along the x-axis quite a bit, but the median error, which is that line in the center, the median stays pretty much nailed at 28 microseconds regardless of the change in parameter, and the interquartile range, which are the lines above and below it, similarly change very little. And even the outliers, which is the first and 99th percentile, which is the top and bottom curves, also change very little as a function of the window size. Similarly, the polling rate, it's an important parameter. We don't want to be overloading our NTP servers nor the network, so we can't be polling too frequently. We see a range of polling periods here. The standard range is 64 to 256. Again, we see the median error, which is that black line, is pretty much nailed at minus 28 microseconds. So what we've got here is a CPU-based, oscillator-based clock. In terms of an absolute clock, it's much more accurate than the current alternative software-based, NTP-based software synchronization, and it's far more robust. I would have liked to have shown you lots of other proofs of the robustness, but I haven't got time for that. In terms of a difference clock, that wasn't even available before. And now we have a difference clock which we use for measuring time differences, which is more accurate than if you had a GPS actually physically attached. And it's extremely robust. It's very important to recognize the need for those two separate clocks. If you want to take advantage of that beautiful smooth rate, you must have a separate clock. It has low computational requirements and could be used. It's ideal for network measurement, but I believe this is really the way to go as a generic replacement for the current solution as well. We have some web resources. There's an old version of this stuff which does not do the absolute synchronization, but does the clock and the rate synchronization for delta T's that's available right now under Linux. And we're working on a BSD implementation for this new work, including the absolute clock as well. Any questions?
Does jitter affect this? Jitter skew certain networks?
The question was, does jitter affect this? I guess you're talking about changes in network delays. Right, so when I say congestion before, that's exactly what I was talking about. So we can filter that very successfully. We also looked, we've tried it with other servers, including a server which was ridiculously far away in another state, which you don't have to go to a server that's a long way away like that, where you have many more hops and much more jitter, much more network delay, and it still performs very robustly.
Thank you very much.